Many students have the knowledge but struggle to communicate it clearly and confidently in interviews. This isn't due to lack of skills but lack of realistic practice and meaningful feedback. And at scale, with over 1.5 million engineering students graduating every year in India alone, this becomes a serious problem. Most platforms focuses only on questions and answers, missing real interview pressure and communication analysis. To solve this, we built Talvo AI, a platform that simulates real voice-based interviews and gives instant personalized feedback.
Now let's take a look on how Talvo AI simulates a real interview experience. In the interview setup, the user first selects the interview type, either a technical round or a final HR round. They can also choose whether to include resume-based questions. Next, the user selects the targeted company, difficulty level, and interview duration. The platform also offers two interaction modes. One, AI avatar with voice, or voice only, after which the system initiates the final interview.
Can you describe the tech stack of Plag? AI, a project you've worked on?
The user can answer the question by using the hold to speak button, or either he can type the text in the text box and send it. The answer is analyzed and intelligent follow-up questions are generated.
You listed Django for the backend of Plag. AI, can you describe how you ensure data consistency across database transactions?
In the technical round, the user selects the company and difficulty level, after which they are given a real coding environment with an integrated IDE. The user solves the problem by passing test cases, and the AI analyzes the code to ask intelligent follow-up questions on logic, time complexity, and possible optimizations.
Welcome to your technical round. Please solve this coding question before we continue. Implement a Python function named solve for, valid parentheses. Return deterministic output for the given inputs. What is the time complexity of the given solution, and how does it compare to other possible approaches for this problem?
Can you explain why you chose to use a dictionary for storing numbers and their indices, and how it improves the solution's efficiency?
After each interview, Talvo AI provides detailed feedback with scores based on knowledge, technical understanding, communication confidence, etc. It also highlights areas of improvements and how to work on them. Additionally, a replay feature allows users to review the recorded sessions and identify mistakes for better improvement. In preference section, the user can edit his profile and also he can update or delete his resume.
Talvo is currently built on an open source tech stack. For the front end, we are using HTML, CSS, and JavaScript, with Django handling the backend and the real time flow. The user's voice input is get transcribed by Whisper and then enriching by a RAG pipeline, which is passed through Llama 3 to generate a smart response. At the same time, an ML model evaluates user's answer. Finally, the response is converted to speech using Cocky TSS all in one seamless loop.
Talvo AI is built using existing technologies like LLMs, Whisper, and RAG, making it highly scalable and cost effective. It runs as a web based platform with minimal hardware needs, easy to deploy for both colleges and individuals. It supports large scale usage with strong practical business model. Talvo AI significantly improves student confidence, communication, and technical skills through realistic mock interviews. It provides data driven feedback, helping identify strengths and weaknesses. With continuous practice, students become placement ready faster, while institutions can scale interview training efficiently with reduced dependency on human interviewers.
Every year, engineering students with flawless technical execution walk into placement interviews and fail. They know the algorithms, but they lose the offer. The breakdown happens because passing a technical interview requires structured thinking and clear communication under direct social pressure. It is a modality gap between how students learn and how they are tested. Universities try to close this gap by scheduling human mock interview panels. These panels provide excellent realism, but they require enormous logistical coordination and cannot scale to test thousands of students simultaneously. This animated diagram illustrates the current trade-off in interview preparation. On the left, the human panel hits a strict availability bottleneck. On the right, traditional online coding platforms scale infinitely, but they rely entirely on text boxes. They completely remove the friction of voice interaction. What is missing is a system capable of evaluating behavioral cues and applying real-time conversational pressure without the logistical limits of human interviewers. A viable solution must combine the infinite computing scale of a text interface with the high-stakes realism of a spoken conversation. Talvo AI is an architecture specifically engineered to close this gap. It achieves this through multimodal orchestration, chaining distinct machine learning primitives together into a single continuous loop. The primary engineering challenge here is speed. To maintain a realistic conversation, the system has to route data across separate models for speech recognition, for logic generation, and visual rendering with near-zero latency. To understand how this operates in real time, we will track a single spoken answer backward through the pipeline. Deconstructing this routing process shows exactly how modern AI tools are stacked to handle complex, real-time enterprise applications. In this pipeline diagram, we start on the far left. A candidate speaks their answer into a microphone, generating the audio waveform extending from the user node. The system's immediate task is converting that unstructured audio into structured text without interrupting the flow of the interview. The audio routes through a Django API into Whisper, a fast speech-to-text model, outputting a text stream. This stream splits into two paths to evaluate different criteria. The downward branch enters a behavioral ML scoring module. This module ignores the technical accuracy of the code. Instead, it measures delivery, tracking communication structure, pacing, and confidence levels based on the cadence of the transcribed words. Traditional compiler tests only care if the code runs. They cannot detect if a candidate stammers, hesitates, or poorly explains their logic. This module captures those exact human metrics. By mathematically isolating the behavioral scoring from the technical evaluation, the system generates a separate, highly accurate feedback matrix for the candidate's communication skills. Returning to the split in our diagram, we follow the top data path to the system's logic engine. If we fed this text directly into a standard large language model, it would output generic coding questions. That is insufficient for high-tier placement preparation. Instead of expensively fine-tuning a massive model for every single company, the architecture relies on retrieval-augmented generation, or RAG. As seen here, the text query bypasses the main model and first pings a vector database, illuminating specific data nodes inside. This database retrieves the precise interview parameters, historical questions, and grading rubrics for a specific target employer, like a FANG system design standard. The system then prepends this retrieved context to the user's spoken answer, fusing them into one massive, highly detailed prompt. Only now does this combined data stream flow into the central logic engine, powered by Llama 3. Armed with the specific company context, Llama 3 simultaneously generates an accurate critique of the candidate's technical logic and formulates the next appropriate follow-up question. Injecting RAG at this specific juncture allows the platform to scale tailored company-specific logic without the severe computing costs of retraining the base model. The final requirement is delivering Llama 3's generated text back to the candidate without breaking the rhythm of a natural conversation. Following the diagram, Llama 3's output text routes immediately to a specialized text-to-speech node running Coqui or Piper TTS algorithms, converting the data back into an audio waveform. These specific TTS algorithms are chosen for their ultra-low latency, which is required to simulate the fast-paced interruptions and rapid responses of a human interviewer. Finally, this synthesized audio routes into the 3D avatar engine, mapping the voice onto a virtual interviewer rendered with Three.js and Ready Player Me, completing the loop back to the user. Providing a visual and audible interviewer forces the candidate to maintain eye contact and react to auditory cues, reapplying the exact social pressure missing from a sterile text editor. Chaining audio ingestion, dual-path processing, and 3D rendering in a continuous loop successfully synthesizes a high-stakes interview environment. Zooming out from the individual easer, we see how this scales. The single loop replicates across a vast server network, processing thousands of parallel streams. Because the heavy lifting is handled by cloud-based machine learning nodes rather than human faculty, the strict availability bottleneck of the university mock interview is removed entirely. This animated grid illustrates the institutional deployment. Thousands of distinct interview pipelines funnel their behavioral and technical data upward into a single analytics dashboard, allowing colleges to track placement readiness across an entire student body. Simultaneously, a direct-to-consumer web platform allows individual students to log on and run unlimited, company-specific practice loops at any time. Deploying this chain of specialized models transitions interview preparation from a localized, manual process into a continuous, data-rich ecosystem. The primary advantage of this pipeline architecture is its modularity. Because the components are cleanly decoupled, new data streams can be inserted directly into the loop. The next phase of development integrates an online IDE directly into the evaluation cycle. By capturing real-time keystrokes and code compilation alongside the candidate's verbal delivery and behavioral confidence, the system will build a complete, airtight assessment matrix. By orchestrating specialized AI primitives into a cohesive workflow, platforms like Talvo AI provide a precise, scalable standard for measuring true technical proficiency.